much, and I'd like to say thank you once again. So, for introduction, I'm from the Vycheslav Institute, and I will be talking about not only about bioimaging, but how to make bioimaging, how to build an instrument in bioimaging, how to make it simple. And before I start, just a few things about what we're doing, why we have this special unit at the Vycheslav Institute, and what is preclinical. What is preclinical studies, just because it is important for the society, because if you reinvent something before it comes to the human, it takes some time, it takes some stages. And certainly if we have now achieved something new before we use it as a drug, we first need to test it in several in vitro studies, and then we test it in animals, and only after that we can help the humans, because if we go directly, so we don't want to kill or make a problem with the humans. And certainly in order to do it, we have focused on this part. We use different instruments, different approaches. First of all, we use animal models, so we need to model different diseases. We also do imaging, because imaging is the most efficient way to approach the problem in the biological organism. And of course, we use state-of-the-art instruments to do it. Okay.
Slava,
no, yeah.
Can you speak up a little?
Yeah, so just hope that you...
Yeah, I'll turn on the mic.
No, it's turned on, but are you here?
No, I just want so the camera can also hear more.
Okay. Okay. Just one, before I continue, the question is the audience, you're from different backgrounds, as I understand. Biology, computer science, maybe. Okay, so at the Vycheslav Institute we have a special facility for that, and this facility is like, let's say we have a perimeter which is absolutely clean, and when we say clean, it's not clean like an Intel, but it's clean means that there is no pathogens inside, additional pathogens, specific pathogens. It's like a hospital, so we have various equipment for imaging, and for my expertise, optical imaging. We have animals that living there. Some of them are genetically modified, some of them they compromise with the immune system. This is why we keep them in the clean area. We have a lot of scientists, a lot of research groups that come in order to have questions. They ask questions, and we try to help them. And actually, this is my primary responsibility. In order to help them, in order to assist them, we have various equipment, as I mentioned, and just to see that we have intravital microscopy, we do a lot of molecular imaging, and we do microsurgery, etc., etc. This is what we do to the people. And of course, I do my own study, I do my own research, and this research mostly I'm focusing on a few areas. I try to put like a map. Of course, it is microscopy. I do microscopy from when I was 5 years old. So I was first, thanks to my mother. So she brought to me as a toy. So I start to play and I cannot stop playing with this. Okay, we do some photonics. We use lasers. Of course, my interest in biology is mostly brain. Of course, blood vessels, and of course, in order to do some analysis, so we do computational microscopy, image processing, machine learning, and of course it's imaging. So we do a lot of imaging. Okay, now about bioimaging. Who was the first scientist as a father of the bioimaging? We go back to the history, probably Leonardo, because he was the first who described the human body, tried to make some paintings and documented what he see. Okay, he was our first scientist in bioimaging as well. And if we talk about bioimaging, let's say just simply divide it into a few levels. Of course, it could be based on the whole organism. We can do imaging on a human or animal. We can do imaging using microscopy on the cellular level, and of course we can do perform imaging using on the molecular level. And maybe I will mention about it a little bit. And certainly when we talk about imaging today, so I would mention about two types of imaging. So we can speak about microscopy, as maybe even without biological background, you may be aware that many physicians, medical doctors, they do static imaging using histology, slides, and microscopy. And I would mention it's static imaging and certainly live imaging, like ultrasound, like MRI, like CT, etc. It also could be live imaging. Okay, still background. Now, before I mention about how to build the microscope, let's mention about what is the microscope and how it looks like. Certainly, if we remember our school, it could be a simple microscope that maybe most of the people, most of the students familiar how it looks like. It's an old-fashioned microscope, still use the mirror, and this is our sample. It's usually, most of the people know, it's like an onion. If we little bit mark the nuclei with the methylene blue or other dyes, so we can see the nuclei. Our, let's say, gate to the biology. This is our toys that we had before, and now we have more expensive toys. So actually, starting from the old-fashioned microscope, now we use advanced microscopy systems like multi-photon microscopy. That the cost of this, together with the laser that we use, about more than $1 million. And this is also Maybach price, about $500,000, and also 700.
What level of resolution do you get?
Okay, good question. When we mention about resolution, of course, we cannot compete with electron microscopy. The idea of, I would not, when I planned this lecture, I didn't want to go to the resolution issue because there are a lot of, could be a lot of time spent. But let's say this microscope can go up to the diffraction limit resolution in the spatial, like XY, and about half micron in Z resolution. But what is good with this microscopy that we can go very deep inside, up to 1 millimeter. So if we talk about what is the benefit of the two-photon microscopy, that it can go very deep in inside the tissue, live tissue, and we can make three-dimensional sections, so not very flat sections. But because today's topic is how to build our own microscope, I will skip it, but let's say there are many publications that we do with this microscopy, but it's not a big deal, because this is advanced system, very expensive, requires a lot of time, expertise. This system that I showed, it's actually you can put the whole animal inside, and you can follow the bioluminescent image. Like, for example, you do maybe you're aware about the fluorescent proteins, yes? Most of them. Okay, we also use the bioluminescent proteins. So bioluminescent, so we can make genetically modified animals or different cells, tissue that will glow at the darkness. So in order to make them glow, we inject luciferin. It's a substrate that will produce the photons inside. So we can take a picture, and by taking a picture, we know where is the, for example, tumor. And what is good with this bioluminescent imaging that, of course, the resolution is lower, but we can use the whole animal. We can see where the metastasis, for example. But the signal-to-noise ratio is much, much, much better. A few orders of magnitude better than fluorescence. And this is optoacoustic imaging that we use light to produce sound, like combine light and ultrasound together. So it could be another lecture what type of the advanced imaging are available, what we can do. But my idea today was to speak about simple system.
I said 1/2 micron depth, but you didn't say the resolution itself.
Diffraction limit, it could be a quarter of the micron. Could be,
for the depth, you say?
No, for the spatial.
For the spatial.
The depth is about 1/2 micron, because the Z resolution is a little bit lower than, and also it depends on where we are. If we're close to the surface, the depth resolution, the Z resolution is better. If we go very deep inside, could be okay. If you still have questions when I finish, I can show the pictures related to the two-photon microscopy if you like it. There are many good images that we have with the two-photon microscopy, even without labeling, but it's another story. Okay, it's nearly, you cannot build it for $10 or $100, fortunately. Okay, before I continue, this is like, if we put a standard microscope, how it looks like, state-of-the-art, fluorescent microscope, and this is like how it looks like the confocal imaging system. So actually it's quite not easy to build and quite expensive. But sometimes standard microscope is not sufficient for some applications. And before I show what we are doing, I like this. Just to mention that I'm around with a lot of expensive equipment that are working well, and I'm spending a lot of time with it. But I like something that you can build by your hands, and I use it in my own research, in my studies. And this is I'm like excited most of the time. And I have also somebody that I like very much. This guy is Prakash. He's from Stanford, Dr. Prakash, a professor from the Stanford University, and he succeeded to build a microscope from a paper. And Ilya mentioned that they also ordered such microscope for a workshop. More than that, he succeeded not only to make it as a toy, but he also succeeded to publish it in the PLOS ONE as a real scientific paper based on this simple $1 microscope. But of course, as I mentioned before, it is for the let's say, for the samples that you put on the slide. You can actually we cannot use it for in vivo imaging. Okay, but what we can do for in vivo imaging, and I would like to show you that we can use something a little bit more expensive, but still affordable. And I call it $100 project, and I just put 4 elements for it. Now I'll explain what is the elements are. Actually, it is LED, light emitting diode, as a one single modality, first modality. Then, of course, we need the filters. This is the most expensive part, so we pay some attention, or maybe find something cheaper one. Of course, we use laser module, like here. Nothing more, something more specific. Sometimes we can. Just you can buy on eBay for $1 up to $5. No need more. And of course, digital camera. This also could be cheap or expensive, and we tested many cameras for that. Then we combine them together. How we combine them together? I will show you first the drawings, how it looks like. So actually, of course, we use lens. Lens also could be expensive, but not necessary. But could be simple. So we have a light source, we have a mirror, we have a filter system, and of course we have a laser that illuminates the animal. And one of the most interesting, intriguing technique that I will start, it's also modality, is use a laser as a, yeah?
I'm not sure I understand. Why do you have both a light source and the laser, both of them lighting on the same spot?
Because it's 2 modalities. We use 2 modalities for different purposes, and I will show why we do. Okay, this we use for fluorescence, the light source, the fluorescent light source like LED, because this is emission, this is excitation filter, sorry. This is emission filter, and this is a mirror to combine both lights together. And this is laser that we illuminate the animal, but not with a single point, but we illuminate it like a diffused light. And then we collect using the CCD camera or CMOS camera. CMOS is much cheaper. And then we have a computer to analyze this data, and I will show how, and I will show what we can get. Let's say start from this. Okay, it's clear for fluorescent, but I will start with this, how we can use laser chip design, or using the laser in order to get information from the biological tissue, from the organism. So this is our, let's say, blood vessel, let's say red blood cells, and the laser source, have CCT camera, and if there is any flow, like red blood cells, if we illuminate the tissue and if there is an emotion, we can, after we collect the images, we can analyze the statistics of what's happened in each pixel on the camera. Okay? So if we analyze these statistics, we can get an image. And I'll show you more precisely. Let's say this is a raw data collected from the surface. Let's say this is mouse here, and this is a raw laser speckle image. So when I say speckles, so I would first, if you look on the laser, there is a pattern around the laser light of interference pattern. So the most physicists, optical physicists, they try to kill these speckles because it's annoying, and it's like the pattern, the interference pattern, okay, around this. So I'm not sure that you see, but it changes on the light intensity, the high or low intensity. And I would, if you still have questions, I would show you some more pictures about laser speckles later on. But let's say we illuminate with the laser the mouse here, then we collect the images, and after we collect the images, we can take one single pixel over time and analyze the statistics. What happens with the light intensity over time? Simple and easy. So this is like a time intensity, and if, for example, we collect images, so and this intensity changes over time, then we use very simple mathematical equation. It's mean, standard deviation. Then we take a formula where we divide the standard deviation on the mean intensity, and after we do it, we have a magic. So, and in this magic, we can see blood vessels. Why it happens? Because of the light scattering. What we collect the light scattering, and light scattering depends on what happens with the scatter particles. So if there is a flow, there is a blurring. I will not go deep into all this physics, but the idea is very simple. So more scatter, more motion inside, more blurring. So, and we have this pattern of the blood vessels. And what is interesting that this, we can see it much deeper inside the tissue than the standard method and the standard microscopy. And still, it's very, very affordable. Laser speckle imaging is very close to the laser Doppler. So laser Doppler, maybe many of you heard, but it's the similar principle, not exactly the same, but very, very close. Much more efficient and much more affordable. Okay, what we can get from that? For example, we can observe what happened with the blood vessels if we induce anything on the blood circulation. For example, we can stop the blood flow and see how it's going on. So this is the video. So what happens? That again, there is a laser for the speckle imaging, and there is a laser to stop the blood inside the blood vessels. So we can get anatomical parameters, we can get functional parameters, and we can use this technique, for example, to examine the photodynamic therapy, like to treat the cancer, to visualize the cancer based on the blood vessels. I'll show how. Okay, this is an example if we use it. Yep.
The last slide. You are using a black and white camera, if I understand correctly.
Yes.
So this you get by combining different pictures.
Okay, this color image is a pseudo color.
Okay.
It's a pseudo color image of intensity based on the intensity, because if you okay, usually the laser contrast shows where the dark areas, where the blood flow is much more intensive, but here we make an opposite, where the blood, the intensity corresponds with the brighter point. Okay, here I'll show you here that maybe here it's much more clear. So we use laser speckle, and compare the standard microscopy, because if we use the standard microscopy and then we want to visualize blood vessels sometime, and this is a tumor, we don't see what is inside. In order to visualize it, we can use very expensive, very advanced techniques, but most of the techniques, if we use, they take a very small area. So the most interesting benefit from it, not just the very simple and very cheap, affordable, but it also can take the panoramic image of everything what is on the area, for example, 2 on 1 or 2 on 3 centimeters. And this is laser speckle imaging, so we see blood flow inside the tumor, and it's about 1 or 2 millimeters depth. So it's clear benefit that we have. And this contrast is based completely on the flow. So we see blood vessels not because of the contrast of the hemoglobin that absorb the green light, for example, but we see it totally because we use the laser speckles and scattering effect. And this is infrared light. Yeah.
Why do we need the speckles and not the light in the center of the light itself?
This is standard light. We don't see anything.
No, I mean, is that because the variance is larger?
The variance where the blood flow is lower, is not larger, is opposite. The variance is larger where is no flow.
No, yeah, but I'm asking, you're talking about the speckles and there is the center of the light.
Center of the light we use specifically to stop blood flow. For example, there we use this as a medical technique, as a therapeutic.
Yeah, but I'm asking if the center of the light, you cannot get this same information, or it's like you get saturation. That's
we use this in other wavelengths. In order to get blood stoppage, we use another. Yeah. I can explain. Okay. Yeah. Sorry.
I think that maybe what Uri was referring to is that what is the difference when you illuminate it with a laser, you get a speckle pattern. If you were to illuminate with a monochromatic LED, you wouldn't get a speckle pattern.
No.
So what does the speckle pattern give you as opposed to just a plain illumination with the same wavelength?
If I use the same wavelength as a plain illumination, I would not see even this. For example, if I use here, I use 780 nanometers as a speckle. If I would use here 780 nanometers as a LED, I would not see anything, because I would not because hemoglobin will not interact with the 780 nanometers. I specifically use speckles where I want to avoid absorption. I want to have a scattering only. And in this case, I use 500 nanometers in order to see hemoglobin. And because the 500 nanometers absorption is higher, then I see a little bit blood vessels, but here I don't see anything. This is a standard illumination. More than that, I can use laser speckle to see through the cranium, because the cranium is also not very transparent. Yes, I'm sorry. May I just I have to be on time, but I show you.
The speckles are kind of modulation of the light.
The speckles is speckles. It's a pattern that it's interference pattern that any monochromatic coherent light produce.
No, but you are using it as a kind of modulation of the light?
No, I don't modulate anything. This is the whole idea. I use $10 laser, put the diffuser, and I can show it on a workshop how it could be done, just taking the laser, making a diffuser, even a paper, illuminate an area of, for example, mouse here, and get the camera. More than that, I can use a little bit high-intensity laser, illuminate my hand, and the laser speckles image that I get will correspond to the blood flow inside. It's like you use a Doppler. It's a laser Doppler imaging system, but it's absolutely simple. The laser Doppler uses the single light and scanning. Here you don't need. And this is the whole idea. And most of the group, they use this laser speckle imaging system as a standalone technique. I use it as a multimodal system. So I need to. May I?
No, it's here.
Okay, this is like benefits. It's very inexpensive. I image blood flow. It's penetration depth. So a lot of benefits and very simple. But we not only use this technique. We also use a combination of this laser speckle with the fluorescence. And I would like to now to go on and just show you what we can do using this laser speckle if we use intact cranium, so we still can see the blood vessels through the intact cranium, and of course we're talking about mouse. And in addition to the laser speckles, we can come with the fluorescence as well. And what is interesting with the fluorescence that we're talking about, that this fluorescence is not a static fluorescence, we use dynamic fluorescence, and if we use dynamic fluorescence, we can get much more information. And we call it dynamic contrast. And I would like to show this picture that we like to use dynamic contrast in order to enhance our capabilities. Now I would like to speak about challenges. What challenges we can solve using this combined technique or standalone technique. And as a first challenge, I would like to speak about the allergy that could be tested using dynamic contrast and fluorescence. And just to remind you, this is what we live in the 21st century, and this is what we do in order to test allergic reaction. Just to show you a little bit biological mechanism, but we were focusing on this acute inflammation, and we wanted to test this acute inflammation using this, at this moment, fluorescent technique. And also I will speak about speckles. I'm sorry for the graphical content. This is how it likes patch test. So the allergen, different allergen should be put on the human body, and then how we test it. Sorry for that.
Allergic for everything.
Yeah, but we don't have a good tool for the humans right now. But more than that, we don't have a good tool for the animals. Like a modern medicine and modern biological studies, they use animals, and in order to test the allergic reaction in the animals, they measure the, let's say, with this state-of-the-art technique, to measure the swelling of the mouse ear. And we wanted to, this test is called mouse ear swelling test, and we wanted to develop as a first, our goal was to develop a technique that could solve this problem. And we came to the conclusion that we can use this similar technique, but we don't need to put a big irritant, so we can put a small drop here, and then we can call up the, we call it dynamic contrast. So this is the fluorescence inside the mouse here. And if the irritant or allergen influence, so we see that fluorescent molecules are extravasate from the blood vessels. And this is, we get this information over time. In order to do it, we use a fluorescent drug, which is non-toxic, and after irritant it makes influence of the mouse ear, the fluorescent molecule extravasate. And we use simple, very affordable technique for that. Okay. We also modified this protocol using several batches on it. So we just our modification. And then we could use 3 substances simultaneously. And this is an example of the mouse here. We use 3 different substances, like glycerol, it does not influence. We use DMSO. This very well known in biology. It's a little bit, and also methyl salicylate. This is also used in the not pharmacology, but yes, it's used in pharmacology and in cosmetics. But it's also mild irritant. I show that this is a fluorescent image. All images are taken with a simple camera and with fluorescence. Okay, so after some time, where was the methyl salicylate? We see the extravasation of the fluorescent drug, and also see a little bit in DMSO. So we can quantify it. So how we quantify? We measure intensity. Okay, and based on this quantification, we can conclude which drug, which pharmaceuticals should be used, should not be used, which has irritative effect or not irritative effect. And this is our first challenge. Okay, another challenge. is a stroke. It's a very, very severe disease that it can cause leading-term disabilities. It's also just some statistics about type of the stroke, and most of the stroke coming from the middle cerebral artery. And the idea was to establish a method based on our techniques, so to visualize the stroke, to image the stroke, and to try to give a tool for the scientists how to treat the stroke. Okay, this is the idea, but of course in clinics people use MRI, PET, SPECT, CT, but it's for humans and it's quite expensive and not necessarily you can get it immediately. So we wanted to follow on the using optical method. So it's also biological but graphical content. This is like a mouse skull and you see nothing through it. And in order to visualize it, so you need to use special techniques. And most of the techniques require drilling or require doing something like during the surgery or using some specific efforts. This is like what people in biology scientists do. So they use either thinning the skull or using the window preparation. And why? Why they do it? Because we have a problem with the optics when we talk about the optics. So usually, if there is a tissue, but we want to see blood vessels, it's hard to see them because we have a scattering. So we cannot get this information as clear if we use, for example, standard thin slice. So the goal is to use some specific techniques in order to recover the image. And how we can do it? What can give us an inspiration? And we got this inspiration from astrophysics. So I have a colleague that came from Observatory of the Paris Observatory, and they work a lot of time already, more than biologists, in order to analyze dynamic information. For example, plasma dynamics of the sun is similar with the dynamic fluorescence in the mouse brain. And working together, we got very interesting results. So I would like to show you some our results. So we call it Transcranial Optical Vascular Imaging, and it is an inexpensive alternative to other techniques. And this technique was based on exactly what I talked a little bit before, on the combination of the laser speckle imaging, and we use laser speckles as a reference, and with the dynamic fluorescence, like I showed you on the mouse ear. Okay, now I would speak a little bit about the dynamic, about this technique, a little bit more in details, like I mentioned before, these are speckles. If we illuminate the cranium, intercranium with a laser, we can collect the images, the laser speckle images, use the simple mathematical formula. You can write this code on, we usually use ImageJ, LabVIEW, or any program language, and we can get this image. Very simple mathematics. Okay, this is speckles. Fluorescence again. We illuminate the brain, we collect the images, the changes over time, and we can analyze them. And we use computation, enhance images, and recover the images. I'll show you a little bit more in detail. So, in order to do it, we inject fluorescein. Fluorescein is very well-known drug. We collect this, illuminate with fluorescent, with LED, and collect images. After that, what we do after that, we collect the images. We use some filtering, adaptive filtering. I would not speak, I see that here. And then recover the information based on the time indexation. And the colors means when the material appears. Okay, let me show you it here. When we inject the material, it first appears in the arteries, and we see it first, and then it appears in the veins, and we see it in the second. And based on the time when the material, contrast material, appears in the blood circulation, we can label them different colors. Okay, this is how it looks like. So we can see blood vessels, we can see arteries. Arteries are red, veins are green, and veins at the late stage are blue. We can detect different, it's normal and abnormal here. So in this case, we don't see here it's okay, and here we don't see anything because of the blood flow problems inside. This is how this method is working. So we can see through the intact cranium, and we also can see through the intact skin. The same. But in this case, we use near-infrared dye. Okay. So, yeah.
Can you combine several cameras so to give a complete image from all sides of the brain?
Absolutely. We specifically work on it right now. We've got the results already pending and also submitted to publications about it. So this is like a conclusion what we can do using this method. I also can combine them, see the tumor model, and of course we can see using this combined technique blood-brain barrier function. And I would say that as a conclusion that this method is first of all informative, can give a functional information, and of course it is absolutely inexpensive. Certainly our next plan is to do exactly 3D imaging, and I will show some results, how it looks like as a video. Okay, this is blood vessels, which is 3D when we try to collect with different perspectives. Okay, I showed you some animal applications, and of course our next goal will be to think about how we can apply it on a human, and it's still challenging. Actually, this is the whole idea that I wanted to talk to you, and I'd like to acknowledge some of my colleagues that I collaborate with, Guillaume from France, and Professor Igor Miglinsky, and Alon Harmelen. He's the head of our department, and he's very enthusiastic, and of course my colleague that work with the microsurgery. And thank you very much for listening, and I would be happy to answer your questions. Thank you very much. Yeah.
So it seems that a lot of the work is actually image processing through, as you said, ImageJ or other applications. How open source in your mind is that? You say it's very simple, but unless
I can show you a code in ImageJ.
Right.
ImageJ is absolutely free. It's open source, and the code is about 60 lines.
Okay.
And it's you collect the data, and I have different variation of the code on ImageJ that I can give you. You can use it and also modify it. And actually, it's based on the procedure. So you just take a stack of the images and take, they call it standard deviation and mean intensity, and divide standard deviation and mean intensity. That's all. And it works simply like for example, I collected 500 images, and ImageJ on a standard computer does it on a few seconds. Okay. If we talk about ImageJ, MATLAB can do it as well, or I also have on a MATLAB, or for example, it could be on LabVIEW. On the LabVIEW, what is good in the LabVIEW, it's not open source, but LabVIEW can do it on fly. So I can acquire image and immediately make processing, and you have an image like real time. Okay. Yeah.
Can you develop it so that let's say you take a mouse and you do this kind of photo imaging,
Yeah.
and then take the same mouse 6 months later on, okay? And you do the same. Can you overlay one on top of the other and only highlight the differences? Only
Yes.
highlight.
It's more image processing.
Oh.
It's more image processing. But also, I just did mention that laser speckle imaging could be used on the humans for free. You can take any camera, laser, and you can use it on a human, and you can, for example, acquire the pulse, any changes in the blood flow, and there are a few companies that already commercially sell such products based on the laser speckles, but it's very cheap to build yourself. Even on there are a few publications people also do it on the smartphone. You can use your smartphone for that. But I don't like a smartphone because the camera on the smartphone, for me it's more hard to control the exposure time. It's better. There's some web cameras that you can control the exposure time.
Also, with such a camera, you have the colors, which which reduce your resolution.
It's reduced the resolution, but it's not a problem if you are limited with the money. It's not a problem because you still can get an image, good high quality image on a standard web camera, which is color. But of course, there are some black and white cameras that also could be more preferable, but not necessarily. There are a few. Let's say, after I didn't pay attention that what I'm doing is important, only after that in Texas they published a good paper that you can use a web camera, and they just published in a scientific journal. And it was shame on me that for 2 years I spoke about it, but I didn't pay attention that I can publish it. But they published it. It's Andrew Dune. He's very nice and much more successful in this. Okay.
Huh?
Yeah.
We have a question online. Eshel is asking, can you think of a pathology that home users could diagnose using a small chip device or phone camera modification?
Yes, absolutely. And there are one group in Ben Gurion that I know. They try to use the cell phone and the laser, and also in the SPIE, in the Photonic West, there are now maybe 10 groups that are trying to do it.
To do diagnose what?
No, to try to build the system.
Yeah, but what could you diagnose with it? The question is.
At the home, you can the pulse, measuring the pulse using the laser is much more efficient than the standard LAT. And there is a company in Rehovot. The name is Fitech. Yeah, I know them. And they use exactly they call it. Actually, I had some complication with one of the founder that they use dynamic light scattering. So they don't use imaging, but they use dynamic light scattering, the signal coming from the laser speckles, and they analyze this pattern in order to make a lot of diagnostic predictions. And now, after they did, I'm not sure that they. But what is good, they now work for many other companies that is trying to measure the pulse, and using the laser is more efficient. Yeah.
Actually, 3 questions.
Yeah.
One, I'm not sure I understand the interaction between the specters, the laser specters, to the fluorescence material.
Yeah.
That's one thing. The other one is about the depth of the cornea. So mouse is probably much thinner than the human brain. So that's
Absolutely.
another one. And the third is about patents. I didn't realize what we can do, at home, but what we can do potentially commercially.
No, if you like academia, it doesn't influence. If there's patents, no patents, as academia, you can do whatever you want. Or if you are doing it at home, you don't need to ask questions.
But if you want to do it like commercially, in a way?
Anything that is public knowledge cannot be patented.
But it's already patented, that's what he said.
No, it's just they.
No.
So first, in the Weizmann, if I do something, they ask if they could be patented, and then we submit it to YEDA, and YEDA then deal with this. But as I'm from academia or as a public, you can use whenever you want. You can build yourself. You don't need to ask a permission for that. If you do it for yourself, or not for the retail or resale, for academia as well.
You need to search yourself if there are relevant patents. No one.
No, but if it's pending, then you wouldn't know. But it's
No,
situation over the world.
I'm not actually, because of the lot of efforts from other groups, I'm not actually, there are many groups that already speckles try to patent speckles. And actually every company that come on the market, they use their own patent and they ignore other patents. And there is no big dispute because it's not a big company. It's actually I know a few of them. There is from Sweden one company. Then there is not a big problem. Your question about combination of speckles and fluorescence I showed, but I can show again. Here is actually it's another story when. To speak about where I combine them, but because we're already over time, but I have many publications where I specifically combine them. This is just one example. It's a speckles, and this is a fluorescence. So I use the speckles as one modality, and then I overlay on another modality. And this is just one example. And also we have a lot of different examples when we combine. And also for the TOVI itself, as it was published as a combination modality. There are many, but it's more technical information, more let's say biological. The speckles is a little bit easier to use. They have some limitations. So actually we use the speckles for navigation and fluorescence in order to make a final snapshot.
So it's not interaction, it's additive combination. It's
additive.
image processing.
Yes, it's
not physical.
And we do it simultaneously because of the filters cube. And we can do simultaneously speckles and
with the same camera?
Yes, absolutely.
You are switching between filters or what?
No. Sometimes yes, but finally now we can use also combined cameras, so we can do one camera for speckles, one for, and if we use one camera, we do iterative process. So we can either synchronize first fluorescence, then speckles, fluorescence, speckles, or first we do speckles in order to navigate where we are. We get the picture of the speckles, and then we use fluorescence in order to get final nice picture. And then we can combine them, overlay them. And your final question was about humans. Yes, using the speckles and fluorescence, we can do it during the surgery on the brain when there is no cranium. It's clear, and in order to see through the cranium, it's very challenging because the mouse cranium with the skin is about 4 millimeters. Here we have centimeters, and we are not yet there. Don't expect magic from the $100 project yet.
Same issue. Even with the mouse, you don't have a problem of signal to noise, very low intensity, and a lot of noise from the camera and so on.
All the problems that we have, we try to solve them based on the step by step. We have a problem of the motion artifacts. But we try to fix immobilized. We also have a problem of the camera, but because we make some averaging, we're solving it, and also we have some Fourier filter, but it's not on this example that I show you. Here we don't use any super sophisticated.
But averaging doesn't solve the issue of signal to noise.
Where?
And with 4 millimeter thickness,
okay.
What is the intensity you can get?
Thickness, we solve it by using infrared dye. And with infrared dye, then we use, I showed you the sun. So actually now we more and more introduce more complicated computation in order to get information and do phase retrieval. But this is our next, it's not for this talk. It's much more interesting afterwards. Yeah, sorry.
Is there a specific reason in wounds? A big issue in wounds is blood flow. Is there a specific reason you didn't mention it in the possible applications?
Wounds?
Yeah, wounds.
Laser speckle images are perfect for wound we have a publication, and also there are many publications where people use standalone laser spectral imaging for wounds. And fluorescence kinetic also could be used for wounds. So as a combined tool, it's perfect, and it could be used on humans today. More than that, you have approved dye, ICG, the sign in green, together with laser speckles, could be used today on humans. And maybe the cost of this system will not be $100, but not very expensive. And also, there is no problem to build it from scratch. For wounds, for burns, and also for diabetic. Yeah, it's also both techniques. Speckles could be used readily, and also ICG, fluorescent imaging also could be used. There is also one of the companies also selling this ICG system.
One more question related to that. Doesn't infrared light increase blood flow? I remember reading some studies related to that. So if you use infrared light,
when you say infrared, you should be correct, because I use near infrared at the intensity that it should not influence the blood flow. It's about 5 milliwatt, 10 milliwatt on the surface. The intensity, but of course, high intensity should increase the blood flow.
Can you say a little bit more in terms of diabetes? How is it useful?
Diabetic, there is a problem with diabetes with the leg, that the blood flow is not sufficient, and it should be diagnosed, and diagnosis is not very, should be done and based on the imaging approach. And this, using ICG and injection of the fluorescent probe is very efficient for that. And there is a lot of studies about it. And also ICG is used during the normal surgery in order to visualize the blood flow in heart, to see the lymph nodes, and also during the brain surgery. It actually could, this combined technique, I'm not claiming that nobody is using it. People use ICG, people use speckles, and I'm just showing more applications for this, also on the humans, also but I show on the animals. Yep.
In the plot you've shown where you extract the mean and the standard deviation,
yeah.
What is the approximate sampling rate, and what is the sampling duration to get a good signal?
Okay, good question. Okay, there is. I'm not talking about physics. I'm just show. Usually we collect one image is 10 milliseconds. It's exposure time, and we collect 30 frames in order to get one stack of frame stack. So 30 frames is enough to make one image, and then we take let's say 500 or sometimes 600 images to get a very nice laser speckle image as a result. So 10 milliseconds for the brain, 50 milliseconds for the mouse ear, 30 frames to get one image, and then we average, for example, totally 300 or 600 images.
So 10 milliseconds per exposure, but at what rate?
It would rate 50 frames. Okay. If 10 milliseconds, it's 50 frames per second, but usually camera gives a little bit lower, so even we can get 30 frames per second, or 30, or 25, it's also good. It's not an ideal situation. The best will be to have 1,000 frames per second, but we don't think it's a little bit more than, okay. It's much better quality, but the price for the fast camera is much stronger, but much more expensive. But it's good to use fast camera.
Is there an importance to the camera's bit depth? Do you think that 8-bit is good enough?
8-bit is enough.
Okay.
8-bit is enough to get this image. 8-bit is enough, but certainly bit depth is, if you have much faster camera, less noisy, the images could be much better. But then it's the price that you pay will not make for some scientific purposes, yes, but for the practical purposes of the microscopy, even 5. So we use 512 pixels per 5212. So, and bit depth is 8 bit is enough, but 12 bit is better. Yeah. Yeah.
You said something about the rate you take the pictures, that you have 30 frames per second. Can you use 2 cameras simultaneously with a little bit of phase between them to get 60 frames?
Yes, we did it.
So there's no real limit. You can use 3, 5.
Yes, we have a continual improvement using few cameras, and so I don't have people and time to write about all the stuff that we already made in order to have phase diversity, 2 cameras, so we have 3 cameras, so we have all different, but the biological questions, without biological questions, I cannot go to the good journal. So without good journal, so what should I can, so there are a lot of curiosity that we have. We tested different cameras, but now we do now more computation and simulations, and it works also good on the computer, and also on open source software.
Functional brain imaging? Functional brain imaging?
Functional brain imaging using speckles are very well established, and people do in order to see different cortical activation. For example, Whisker system. They can also, now we thought to combine it with the fluorescent system. But Whisker system using speckles is very well established, especially in the States.
How it's called, by the way?
What?
This method specifically for brain imaging? Is there a name for it?
Laser speckle imaging or laser contrast imaging, and then you see functional. You can see cortical activation using laser speckle imaging. There's Andrew Dune, also Andrew Dune that I mentioned, David Boas, but now they little bit. It's quite. When I started, it was 10 years ago. Yeah, it was 10 years. Now it is becoming more common and robust method, laser speckle. But most of the people don't combine it with anything else. So I try to. My pioneering was to combine it with fluorescence and use much more biological applications when this combination is useful. So we have many publications when this combined method working. Not only speckles, but also with the fluorescence. And not only standard fluorescence, but now I'm interested in dynamic fluorescence. But we can get more information because of the time that we analyze the few images, not all one image, but few images. Yep. Yeah, okay.
Can you use this kind of imaging to view organelles inside animal cells?
Speckles are also, they call it dynamic light scattering microscopy, where you can use but not infrared laser because of the size of the speckle. We can use UV laser or green laser in order to follow up the dynamics of the organelles inside the single cell. It's possible. And also this work was done 5 or 6 years ago. And actually, they also fluorescent speckles, but I'm talking about this dynamic light scattering. So there's a fluorescent speckle imaging, and there is a dynamic light scattering microscopy. It's a little bit two different microscopy approaches. Because fluorescent laser speckles, they are more like confocal, used for grid illumination of confocal. Yep, this.
Thank you.
Yeah.
One last question.
Yeah.
So if for these companies trying to develop a mobile application, could laser speckle imaging be used in ambient light, or you would have to have some sort of shield like protecting your skin?
if you use combination of the infrared light and good combination coupling of filter and laser, the ambient light could be not as strong, not a problem. But sun is. But actually, you analyze the fluctuation with the speckles. You analyze the fluctuation. You want to DC. You want to remove, so you don't need it. Yeah. Okay. Yeah.
If you go back to one of the first slides where you shown the two light sources, the beam splitter and both filters, I think that in most of this talk you've only mentioned laser and camera. And is the extra LED and extra filter specifically for the fluorescence?
Yes.
Okay.
This is both. It's just schematic that. Actually, I can use not only LED, I also use the standard UV lamp, but also LEDs works perfectly. The filter, this is the excitation filter, this is the dichroic mirror, or actually you can use also oblique illumination. And this is emission filter, and both, it can work for the fluorescence and it can work for the laser module without interfering. Or you can specifically take another filter and split for another camera, but then a little bit more expensive, but actually it also works. So the filtering is like, it's very simple design. You also don't need to use it. I mean, you can make two light sources from the side, and it also works nice.
Thank you.
Thank you.